Welcome back. So we are meeting after a gap of 2 weeks, and now we are ready to study the second law of thermodynamics. The second law of thermodynamics is perhaps the most important part of thermodynamics. In this series of lectures, next 2 to 3 weeks, we will be studying the second law and some aspects of second law. We will quickly revisit the first law and the zeroth law, what they tell us, what they do not. We will in particular look at the status of temperature. Then we will visit history, look at the statements of the second law as proposed by Carnot, Kelvin, Clausius and Carathéodory. Our primary statement will be the Kelvin-Planck statement, and we will see the reason for that. Then we will define some useful terms which will simplify not only our discussion but our algebra and calculus. These will be the heat engine, the efficiency, the thermal energy reservoir and a lot more. And we will have lots of derivations and definitions to work with. In the remaining of this lecture, let us review something which we have studied. Let us look at the first law, revisit it. Using first law, we have defined energy and the heat interaction. There is no place for temperature in the first law. Temperature came later when we studied the zeroth law. Then we can consider the first law as a statement of conservation of energy, because it tells us that energy can only be transferred from a system to another system through the work or heat interactions. It cannot be created out of nothing. And remember, there is nothing directional about the first law. The first law does not tell us in which direction a process may take place. Let us look at this limitation of the first law. Let us say that if we have a vessel containing water and we have a stirrer in it, and the stirrer is in contact with a cold plate. So when we stir it, some stirrer work is done, it is negative as we know, and because this W is negative, the energy of this system will tend to go up, its temperature will tend to rise, but then we allow heat transfer from the system to the cold plate and adjust these two interactions, work being done here and the heat transferred here, both negative numbers, then it is possible that the change in the energy of this system and the change of state of this system is 0. So remember that here the stirrer work is negative, the heat transfer is also negative, and it turns out that there is no change in energy, and this we see is possible in practice. But the first law simply says that delta E, in which case, in this case it is 0, is nothing but Q minus W, and since only stirrer work is involved, we can say this is Q minus W stirrer, and both of these are negative quantities. The first law is satisfied even if you change the sign of Q and W, make them positive. We can assume, for example, that Q is positive, it absorbs heat from the cold plate, and we can also assume that W stirrer is positive. This equation would still be valid with W stirrer greater than 0, Q greater than 0, delta E still be 0. But we know this does not take place in practice, although it is okay by first law. This is one of the limitations of first law. First law is an equation, you multiply both sides of the equation by -1, changing the directions of all interactions, and changing the sign of energy change if it is non-zero. Okay, and first law would say that the process is still okay from the first law point of view. Now let us visit the zeroth law of thermodynamics. When we revisit the zeroth law of thermodynamics, what we find are the following things. Zeroth law dictates the existence of thermal equilibrium between two systems under certain conditions. It provides us a thermodynamic basis for temperature, which is a label for isotherms, nothing more, nothing less. But remember that we still do not have, using just the zeroth law, a thermodynamic basis for the scales of temperature. The scales of temperature now in use, whether Celsius or Kelvin, they use a property of some material, some liquid, some gas, a supposed ideal gas, and we still have no basis for calling a temperature higher or a temperature lower, except that the numbers given on a particular scale of temperature are higher and lower, but they are arbitrarily given the way we define the fixed points and the definition of the scale. This higher and lower temperature is a limitation. For example, we know in practice that we have a system A and a system B. It is possible that heat is transferred from A to B, and in which case we say that the temperature of A and temperature of B will be such that on our defined scales TA is greater than TB. We also know that if A and B are in the same states as earlier here, then such a transfer of heat from B to A is not possible. This is an observation, but we do not know the basis of this. We should have a thermodynamic reason for a temperature being called higher and a temperature being called lower. We still do not have it after studying the first law and the zeroth law. The motivation for the second law are some facts which are as yet unexplained in our study of thermodynamics, and these are the fact that all natural processes take place only in one direction, and for a process typically there is a situation before and a situation after. We cannot interchange them. In loosely we can say many processes are not reversible. We have not yet defined the term reversible, we will define it formally during the course of these lectures. We also know that there are limits on some processes. For example, if you put in a bucket of water at low temperature something hot, say a hot metal ball or a hot vessel, you know that the vessel cools, the water gets heated up, and after some time the process stops. It does not proceed any further. So this is a limit on process. Then we know that temperatures are higher and lower in some sense, but we do not yet have a thermodynamic basis for this. Now it turns out that the second law of thermodynamics is the one law which provides a basis for the explanation of all these. What will the second law of thermodynamics help us do? The following. First, it helps us determine what is possible and what is not. It will also dictate limits on the behavior of processes and the systems involved in executing those processes. It will provide us a proper basis for the hierarchy of isotherms. a proper thermodynamic basis. It will hence provide a basis for thermodynamic scales of temperature, and this will be a set of scales which we can determine and use without using the property of any material. So, that will be a thermodynamic basis. And finally, it will help us determine a very useful property called entropy. We will give that property the symbol S. And finally, it will help us derive a number of relations between thermodynamic properties. As I have said earlier, thermodynamics does not dictate what should be the property of a given system, but it does dictate the relationship between some properties of systems. It will say, if this is the way temperature varies with pressure, this is the way volume will change with, say, entropy. We will derive a large number of such properties. So, be ready to dig deep into the second law of thermodynamics for the next 3 to 4 weeks. Thank you.